So, in this lecture we are going to look at the tools used for quantifying microstructure. This is an area called stereology, and correspondingly in metallurgy it is often called as quantitative metallography. Now, what is stereology? The term itself dates back to the 1960s, when for the first time this term was invented by metallurgists and material scientists, where it was required to quantify microstructures. Now, what is the problem that was being addressed at that time? The problem is that our metallic structures are opaque, and when we look at a microstructure, we look at a planar section of the structure, while the structure of the material itself is a 3-dimensional structure, and what you are looking at is a microstructure as a 2-dimensional image. Now, from this 2-dimensional image, we have to reconstruct or estimate some of the parameters of the 3-dimensional structure. For example, we have to find volume fraction of a certain phase, then what kind of measurements we must make on our 2-dimensional image to be able to estimate the volume fraction, or if we are looking at size of particles, then we need to make certain kind of measurements to be able to estimate the size of the particles, and so on. So, we will be looking at various measures on the 2-dimensional structure to be able to estimate the 3-dimensional parameters of the structure of the material. So, essentially stereology relates 2-dimensional images of microstructures to the 3-dimensional structure of materials. Quantification of geometrical features of the structure of materials is a key for stereology, and what does stereology provides? It provides mathematical tools to perform this transformation of 2-dimensional measurements on the planar microstructure to the 3-dimensional parameter of the structure of solids. Now, before we go into this, let us try to understand what are the elements of a 3-dimensional microstructure. So, if you look at this image of a block of material, this block of material, it is essentially an abstraction of what kind of geometrical elements that we normally want to estimate. The geometrical elements could be 3-dimensional particles present in the structure of the material. They could be surfaces which are grain boundaries or particle boundaries that would be present. So, this is shown as a surface here, or this could be line elements that are shown here. There could also be points in the 3-dimensional structure, but here we are just going to focus on these 3 elements. So, the typical microstructure elements are 3D particles, 2-dimensional surfaces or interfaces between particles and grains, or 1-dimensional linear features such as dislocations, grain edges, fibers, etc. Now, let us see how we get an image out of this 3-dimensional structure. Well, this is one way we produce an image. We cut a section through the material, and then what we would typically do, if we are going to an optical microscope or a scanning electron microscope, we would polish the surface, etch it to reveal the various elements of a structure like grain boundaries, second phase, and other structural elements. So, if I take a section through my solid and it cuts the various geometrical elements that are present. So, for example, 3-dimensional solids that are present or particles that are present, like ones that are marked in red here, they will get cut into a 2-dimensional profiles or area profiles. So, now they would be shown as 2-dimensional images. A surface, if it gets cut, it will produce a line. If the line elements that are present, like for example dislocations, they will produce points. So, these are the kind of elements that would be present in our two-dimensional image of the microstructure. From such images, we have to make measurements to be able to predict, for example, what is the volume fraction of these particles, or what is the size of these particles, or what is the density of these surfaces, or what is the density of these line elements. Now, this is one way we produce an image. This would typically be done in an optical microscope or a scanning electron microscope. Now, coming to a second way of forming an image, in a transmitted light microscope or in a transmission electron microscope. Here the beam, whether it is a light beam or electron beam, it is passing through a volume of the solid, and we obtain what is called as a projected image. Now, if I look at this projected image, the particles, the three-dimensional particles will get projected as area onto my image. The surfaces would also get projected as an area, and the line elements, instead of being points in the section image, now get projected as linear elements or lines. Hence, the stereology that we develop, the tools that we develop for making the measurements in the section image here is different from the stereology that is used here. The projection brings in some additional complications. However, for this particular set of lectures, we will not be discussing the projected images, we will be only concentrating on the section images, which constitute the large part of our quantitative metallography. The basic elements of interest in a three-dimensional structure, just to summarize, are 3D objects, particles or grains, surfaces of three-dimensional objects or interfaces and boundaries, of one-dimensional linear elements like grain edges, dislocations, fibers. Optical. Now, before I go into the actual tools, let us look at some microstructural images that we obtain from optical microscopes, which could be a reflected light microscope or popularly called as the metallurgical microscope or a transmitted light microscope. But for our metallurgist and material science applications, normally it is a reflected light microscope that we are interested in, because our transmitted light microscope can only be used in those materials which are transparent to light. So, this is one way we would get our microstructural images. Electron microscopes like the scanning electron microscope will produce images from secondary electrons and backscattered electrons, or even X-ray map images. Now, for most practical purposes, secondary and backscattered electron images could be treated as single section or planar section images. However, this may not be true for X-ray map images, where the X-ray is coming from a large volume of the material. The transmission electron microscope would produce projected images. Then you also have many other microscopes like the atomic force microscope and the scanning tunneling microscope. Looking at some of the microstructures, for example, here are a couple of microstructures shown from a metallurgical optical microscope. This is a microstructure of a nodular cast iron, where the dark regions are the graphite nodules, and this is a single phase polycrystalline material showing us grain boundaries, and also you can see where three boundaries meet triple points, which are actually in the three-dimensional image are actually lines or triple edges. So, using stereology, we will see that we can estimate size of these nodules, the volume fraction of the nodules. Out here we can estimate grain size of these on an average grain size using stereological techniques. We can even measure what is the density of triple edges, that is the length of these triple edges per unit volume in the 3-dimensional structure. We can, this is an image of a few perlite colonies in a steel. Here we may be interested in measuring the interlamellar spacing. Again, stereology can help us in doing that. This is just a magnified image of the same thing in an atomic force microscope. Now, these are projected images in a transmission electron microscope of polycrystalline material. This image shows 3 boundaries meeting at a triple edge, while the image at the bottom here shows dislocations, and stereology can be used to determine, for example, the density of dislocation, which is line length per unit volume. Now, let us see how actually stereology is implemented. So, one of the things we need to understand a few terms. One of the terms in stereology are probes, which are used to probe the microstructure, the 3-dimensional structure of the material, or what is called here structure is sampled by probes. And here the sample, the meaning of the sample is in its statistical sense, that we sample a representative volume of the material in order to estimate what is the particular parameter that we want to measure. Now, how is sampling done? Well, one is obviously when you take a section, we are actually sampling the material. So, sampling by a 2-dimensional probe, or what we can call as a plane section or a plane probe. So, when you section it, so intersection of a plane with the structure is a process of sampling the 3-dimensional structure. Second, why with a 2-dimensional plane? We can also section by a line probe or a 1-dimensional probe. We can hypothetically think that we can draw a line through the structure and see the intersection, make some measurements with of the intersection of the line with the structure. We will soon see what it all means. Similarly, I can go down to the 0-dimensional probe or the point probe, which is the intersection of a point with the structure. If I look at this particular image here at the top, we can try to understand what these 3 probes are doing. First is a section we have taken. So, these could be 3-dimensional particles, for instance, and they have been sectioned, and now I have the area profiles. These are lines that you see, which are nothing but the plane probe cutting surfaces in the 3-dimensional structure, and the points are represented by the plane probe cutting a set of lines. Now, what about the 1-dimensional probe? Well, you can see the lines here, horizontal lines or the vertical lines. Now, they are sampling through the 3-dimensional structure. So, for example, I could take these lines and look at what is the length of these lines within the individual particles. So, intersection of a line with a 3-dimensional object, or it could be the intersection of the lines with these linear elements that I see on the plane probe, or these are lines which are actually cutting the 2-dimensional surfaces. Similarly, if I look at the 0-dimensional probe, we can look at the intersection of the horizontal lines and the vertical lines are the points. So, these are the point probes. So, I could see the intersection of the point with the 3-dimensional particles, and we will see what kind of measurements we can make with these intersections. So, going to the next slide, what are these probes doing? Probes interact with the microstructural features to produce events. Now, these events are in the sense of probabilistic events, that is, there is a certain probability of some of these events taking place. For example, interaction of the plane probe with volume features or solid 3-dimensional particles produces 2-dimensional cross section. So, I have a table in which I have given some of the events and what are the kind of measurements I can make on these events. For example, if the feature is volume, which is like a 3-dimensional particle or a 3-dimensional grain, a plane probe will intersect some of these volume features or these particles and produce cross sections that are shown here. One of the measurements I can make on this, among many others, is the area of these cross sections. A surface feature in the 3-dimensional structure intersected by a plane probe produces a line trace. Well, I can measure the length of these lines as a measurement. I can take a linear feature in the 3-dimensional structure like triple edges or dislocations. A plane probe will produce point intersection, and a measurement, a simple measurement that I can make on these points is to simply count them, how many points I have in a given area. Similarly, a line probe with a volume will produce an intercept length. So, if I look at, for example, this horizontal line, it makes an intersection with the 3-dimensional particle, and I can measure this length of the intercept contained inside the particle. So, I can make a length measurement. A surface with a line will produce a point intersection, and I can count the number of such points. For example, if I look at this horizontal line, I have only one intersection here. If I count with this, I have another one. If I look at this, I have yet another one. If I look at this horizontal line, I have yet another one, and similarly I can do these things with the vertical lines as well. Finally, I have a volume feature and a point probe. I have point intersection, and I can make a measurement of counting the number of such points. So, for example, I can count this as one point which is inside the particle. I can count another point like this which is inside the particle. I can count a third one which is also inside the particle. Now, these are the kind of measurements I can make, and then we will see how stereology can be made to relate to the 3-dimensional structure. Now, what are the consequences of the intersection of the probe with the 3-dimensional structure? Well, as you have seen, probe is of a lower dimension than the structure. Like plane probe is a 2-dimensional, and my structure is 3-dimensional, or a line probe is 1-dimensional, or a point probe is a 0-dimensional. So, whatever probes I am using has a lower dimension, and as a consequence this leads to loss of information. For example, a plane probe intersecting a cylinder will produce various kinds of profiles. For example, it can produce circular profiles. If the plane probe cuts the cylinder perpendicular to its axis, it will produce an elliptical profile. If it cuts at a angle to the axis of the cylindrical particles, and I may not be able to tell from the various shapes that I get that these are actually cylindrical particles. So, this is what it means, that one of the things that I lose is information on shape. That makes sometimes analysis difficult unless we assume a certain shape. For example, the graphite nodule microstructure I had shown, if we assume them to be spherical particles as an approximate shape, then I can go ahead and perform certain stereological analysis. Stereological methods are statistical in nature, and hence they will be subjected to statistical errors, and we have to obtain average estimates. That means we have to cover large enough area in the sample to get a good average estimate of the 3-dimensional parameter. And most importantly, stereological methods have mathematical rigor. and that we will see soon. Some of the relationships that you may see in some of the classical relationships of stereology appear to be very simple, but they have been rigorously derived. So, we have already seen the stereological operations which are produce events in stereology, which is the interaction of probes with structure, and we will now see that these events have a certain probability. That what is the probability of a particle getting intersected by a plane probe? What is the probability of a point falling inside a certain phase, inside a certain kind of particles in the microstructure? And hence we bring in the concept of geometrical probability, which is no different from our classical definition of probability, as we shall see. So, I am going to consider some hypothetical experiments. Let us consider, these are all thought experiments. So, this is consider experiment number 1, it is done on a 2-dimensional plane. Let us consider a 2-dimensional box, a square box of size L by L. Inside this box I have a shape, a circular shape of diameter d, and I randomly put a point anywhere inside this box as represented by such a point. Now, this point I have just made it, exaggerated its dimensions to clearly show it, otherwise this point has to be considered as a 0-dimensional point which has no size. Now, the question that I ask is, what is the probability of intersection of this point, or what is the probability of this point falling inside this circular shape of diameter d? If we think about it a little bit, it should become evident that the probability of the point falling inside the circular shape is nothing but the area of the shape, area of the circle divided by the total area of the box containing the shape. Hence, the probability is nothing but pi d square upon 4, that is the area of the circle, divided by L square, which is the area of the box. And if you look at what is this ratio is actually nothing but the fraction of the area occupied by the circular shape inside this box of area L square, and this on the right hand side I am calling it as area fraction. Similarly, I could go to a 3-dimensional space as experiment number 2, where now instead of a circular shape, now I have a spherical shape of diameter d inside a box in the shape of a cube of dimensions L by L by L. And again I ask, what is the probability of a randomly placed point inside this cubic box, that the point will fall inside this spherical shape? And this is an analogous problem to the 2-dimensional problem on the left. Instead of areas, now we are talking about volumes. So, the probability of a point falling inside the spherical shape is nothing but the ratio of the volume of the sphere to the volume of the cubic box, and which very clearly then the probability would be pi d cube upon 6 divided by L cube. And if you look at it, this ratio is nothing but the fraction of the volume occupied by the sphere inside the cubic box, and this is what we can call it as the volume fraction. This can, or both of these results can be proved rigorously, but I am going to skip in these set of lectures the rigorous proof behind them. A third experiment in geometrical probability could be that now I have a sphere inside again a cubic box, and I asked the question, what is the probability that if I place a random section, I cut this randomly in such a way that the cut is made parallel to this particular face, but that cut can be anywhere along this. So, I could make a cut here, I could make a cut here, or I could make a cut here, and it is a randomly placed cut. The question of probability here is, what is the probability that a random cut will cut this spherical particle? Now, in order to look at this, consider these two planes which have been drawn in such a way that they are tangent to the opposite ends of this spherical particle. So, this plane makes a point contact with the spherical particle on this side, and this plane makes a point contact on this side of the particle. What would be the distance between these planes? The distance between these two planes would be d. So, the probability of a random cut parallel to these tangent planes would be, intuitively we can guess that it would be nothing but the ratio of this length versus the total length, which is nothing but the ratio d upon L. Similarly, let us have another experiment where now I have a line probe which can be randomly placed anywhere inside the cube, but keeping it parallel to this vertical edge. There is a spherical particle present, and the question again is, what is the probability that this line probe will intersect the spherical particle of diameter d inside the cubic box of size L by L by L. Well, this problem can be reduced to actually experiment number 1 of the point being dropped on a two-dimensional plane, and how? Well, project the spherical particle onto the bottom plane. The projection will show up as a circle. Now, this random location of this random line is nothing but the location of the end point of this line on the on the surface on which we have projected the spherical particle. So, therefore, this line will intersect the sphere if this point, the end point of the line, falls inside the projected circle. Hence, the intersection of the line with this spherical particle is nothing but the area of this particle divided by the area of this plane, and hence the probability of the line intersecting the spherical particle is nothing but pi d square upon 4 divided by L square. Consider yet another experiment in 2 dimensions, and I leave this to you to work this out. Probability of this line intersecting this circular object in this 2-dimensional box of L by L is nothing but the ratio d upon L. We look now at a couple of more experiments. With the one I am looking at is now take a non-spherical object. Here, what would be the probability of a random plane parallel to this face of the cube cutting this non-spherical object? As you could see now, the 2 tangent planes that I have drawn, the distance between these 2 tangent planes would depend on what is the orientation of this non-spherical particle. So, this the distance h between these 2 planes is now going to vary with the orientation of this particle. Now, the question is, what is the probability of a random plane cutting an object which also takes up a random orientation? If it was a fixed orientation, then the probability would simply be h, the distance between these 2 planes, which is also called as the tangent diameter of the particle, divided by the total length L. But since the particle also takes up a random orientation, the probability, then we have to consider what is the average tangent diameter of this particle. The mean tangent diameter of this particle would be, we have to take average of all possible orientations of this particle. Hence, the probability would be equal to h bar upon L, where h bar is the mean tangent diameter.